Hey everybody, welcome back to Intermediate Algebra. Today we are in section 10.1 and we're starting our final chapter of the course. We're going to do sections 10.1 through 10.5 and that's going to finish up the course for us. And so today we're talking about radical expressions, and these are the things we're going to tackle. These are our objectives. We're going to talk about finding square roots. We're going to determine whether a given root is rational, irrational, or not even a real number at all. And we're going to talk a little bit about cube roots and fourth roots and other roots. We'll talk about the nth root of the nth power, and we'll even use a calculator to find roots. So that's a lot. Let's go ahead and get started. First of all, what do we even mean when we say square root? Well, you remember that squaring a number means to multiply that number by itself. So the opposite or inverse of squaring a number is taking its square root. For example, 1 square root of 49 is 7, because 7 squared is 49. Therefore, we can say that the square root of 49 is 7. Basically, the square root undoes the squaring function. So here in example 1, they're asking us to find all square roots of 64. So the word all is kind of a clue that we're expected to come up with more than one. So remember, the square root of a number is a number that you can multiply times itself to get that original number. So for 64, we're looking for a number that we can multiply by itself to get 64. Well, we know that 64 can be written as 8 times 8. But if you think about negative numbers, 64 can also be written as negative 8 times negative 8. So both of these numbers are considered square roots of 64. So we'll go ahead and say the square roots of 64 are positive 8 and negative 8. Now I'm sure you have seen the square root symbol before, and what you need to understand is that the square root symbol only represents the positive square root of a number. So the positive square root of a number is written with this symbol, and this is called a radical. This square root symbol is called a radical. The expression that's written under the radical is called the radicand. And again, it's really important to remember that the radical indicates only the positive square root of a number. If you want to indicate a negative square root, then you have to have a negative in front of that radical symbol. For example, the square root of 81 is 9. When we write it like this, with the 81 under a radical, we don't consider the negative 9 because the square root symbol, the radical, only will give us the positive. If you want to talk about the negative square root of 81, you have to have a negative in front of the radical. So negative square root of 81 would be negative 9. See how this works? Positive square root of 81 is positive 9. Negative square root of 81 is negative 9. Okay, so continuing with that idea, let's generalize that. Let a be any positive number, and then the square root of a is the positive square root, or we call it the principal square root because it's like the main one. And then the negative square root of a is like literally that. This represents negative square root of a. So from there, for any non-negative number a, we have this. The square root of a times itself would be written this way, and that's just equal to a. So what you see here is that the square root and the square undo each other. We say that the square root is the inverse of the square, and so basically they cancel each other out is how you can think of it. So the square of the square root of a is just a. And also, if you have negative square root of a times itself, that would be written this way. And again, negative times negative is positive, and square root of a times itself is just a. So this also comes out just equal to a. And then also we have the square root of 0 is equal to 0. Now let's practice evaluating some square roots. So here we have square root of 144. Well, we know that 12 times itself is 144, so the square root of 144 is 12. And we only have the positive 12 here because we have the radical symbol. And remember, that always represents just the positive square root. Here in part B, we have negative square root of 225. So 15 times itself is 225. So the negative square root of 225 is negative 15. Then on part C, we have square root of 4 over 9. Now both of these numbers are perfect squares, and so 4 is 2 times 2, 9 is 3 times 3, and so the square root of 4 over 9 is going to be 2 over 3. Because think about it, 2 times itself would be 4, and 3 times itself would be 9. Alright, on part D, we have negative square root of 16 over 49. So again, both of these numbers are perfect squares, and we have this negative in front. So the negative square root of 16 over 49 is going to be negative 4 over 7. Now in example 3, it says find the square of each radical expression. So notice all of these are already under radicals, and it doesn't say find the square root, it says find the square. So for each one of these, we'll put it in parentheses and square it and see what happens. So we have square root of 13. If we square that, well, we know that the square and the square root undo each other, and so the square root of 13 squared is just 13. On part B, we have negative square root of 29. So if we take this expression and put it in parentheses and square it, the negative times itself is positive, and the square root of 29 times itself is just 29. So we end up with positive 29. For part C, if we take this expression and square it, we have the square root of p squared plus 1, all squared. Again, the square root and the square cancel each other out, and we are just left with p squared plus 1. Now let's talk about how to decide whether a root is rational, irrational, or not real. So first, we need to recall what rational means. Rational numbers are numbers that can be written in a fraction form. So of course all integers are rational numbers because any integer can be written with a denominator of 1, and that's a fraction form, and therefore it's rational. And I think on one of the previous slides I used the term perfect squares. So numbers with rational square roots are called perfect squares. What are some examples of perfect squares? Well, 1 times 1 is 1. 2 times 2 is 4, so that's a perfect square. 3 times 3 is 9, so that's a perfect square, and so on. 16, 25, 36, 49, all of those numbers are perfect squares. Anytime you do a rational number times itself, the answer to that calculation is a perfect square. On the other hand, numbers that cannot be written in a fraction form are called irrational. So if a is a positive real number that is not a perfect square, then we say the square root of a is irrational. Here are some examples of irrational numbers. The square root of 2 is irrational because there's not a rational number times itself that will give us 2. So square root of 2 is irrational. Square root of 3 is irrational. There is not a rational number times itself that will give us 3. Square root of 5, square root of 6, square root of 7, square root of 8, we could go on. Square root of 9 is 3, so the square root of 9 is rational. The square root of 10 is irrational, and so on. So we've talked about rational roots and irrational roots, but we also need to know that not every number has a real number square root. For example, the square root of negative 36 is not a real number, because there's not a real number that we can multiply by itself to get negative 36. The problem is that when you multiply a real number times itself, you get a positive. So there's no number that I can multiply times itself to get negative 36, therefore we just say it's not a real number. So let's identify the type of square root. It says determine whether each square root is rational, irrational, or not a real number. Okay, square root of 17. Well, there is not a rational number that I can multiply times itself to get 17. So we're going to say that the square root of 17 is irrational. For square root of 64, there is a rational number I can multiply times itself and get 64. 8 times 8 is 64. So this square root would be rational. And for square root of negative 25, there's not a real number that I can multiply times itself and get negative 25. For example, negative 5 times negative 5 is positive 25, and positive 5 times positive 5 is positive 25. So there's no real number that will give me negative 25 when I multiply it times itself, so this square root is not a real number. Now let's talk a little bit about cube roots, fourth roots, and so on. If the square root is the inverse of squaring a number, then the cube root is the inverse of cubing a number. And to indicate a root besides the square root, we use an index on the radical. And an index is just a little number that goes in the crook of the radical that tells you which root you're working with. Now, if you're going to have to work with third or fourth roots, it's helpful to know a few of the third and fourth powers by heart. That way, when you see those numbers, you'll automatically recognize them as a third power or fourth power of some smaller number. So let's look at a few. 1 to the third power is 1. 2 to the third power is 8. 3 to the third power is 27. 4 to the third power is 64. 5 to the third is 125. 6 to the third is 216. 7 to the third is 343. 8 to the third is 512. 9 to the third is 729. And 10 to the third is 1,000. Now, if you're asked to evaluate the third root of one of these numbers, so for example, if I said, what's the third root of 343, you would say 7. What's the third root of 8? 2. What's the cube root of 27? 3. Third root, cube root, those terms are interchangeable. What's the cube root of 1,000? 10. Okay, let's do the same thing for the fourth powers. The fourth power of 1 is 1. The fourth power of 2 is 16. The fourth power of 3 is 81. The fourth power of 4 is 256. Fourth power of 5 is 625. Fourth power of 6 is 1,296. Fourth power of 7 is 2,401. The fourth power of 8 is 4,096. Fourth power of 9 is 6,561. And the fourth power of 10 is 10,000. And now let's look at example 5. So we're going to be finding a few cube roots. In part A, we have cube root of 8. So we need to ask ourselves, what is a number that you can raise to the third power and get 8? Well, 2 to the third power is 8, so that means the cube root of 8 is 2. And now let's look at part B. So we have cube root of negative 8. Now we don't have the same problem with the cube root as we did with the square root. When we did the square root of a negative number, we saw that that number was not real. But when you raise a negative number to the third power, you get a negative result. So the cube root of a negative number is just another negative number. Here, what is a number that we can multiply times itself 3 times? In other words, what's a number that we can raise to the third power and get negative 8 as our answer? Well, of course, that is negative 2, because negative 2 raised to the third power is negative 8. Think about it. 2 times 2 times 2 is 8, and negative times negative times negative is negative. So that means the cube root of negative 8 is negative 2. Now, how about the cube root of 216? Well, we know that 6 to the third power is 216. So the cube root of 216 is 6. So let's look again at what happened with part B of that last example. We were able to find the cube root of a negative number. So just like we saw with the square roots, when a radical has an even index, the radicand, the number under the radical, must be positive in order for us to get a real number. But when a radical has an odd index, a negative radicand will just give you a negative root, and all positive radicands will give you positive roots. So let's practice here. We have the fourth root of 16. So what is a number that we can raise to the fourth power and get 16? Of course, that would be positive 2. And on part B, we have the negative fourth root of 16. Now notice the negative is not under the radical, so we're not going to have any problems with not being able to get a real number. The fourth root of 16 is 2, and there's a negative in front. So the negative fourth root of 16 is negative 2. Here in part C, we do have a negative under the radical, the fourth root of negative 16. So we're trying to ask ourselves, what is a number that we could raise to the fourth power and get negative 16 as the answer? And of course, there's not a real number that will do that. If you take a real number and raise it to the fourth power, you'll get a positive answer. So the fourth root of negative 16 is not a real number. On part D, we have the negative fifth root of 32. Well, we did not look at the fifth powers, but I don't think it will be very hard for you to realize that if 2 to the fourth power is 16, 2 to the fifth power is going to be 32, because 16 times 2 is 32. So the fifth root of 32 is 2. So we have negative 2 here. And then on part C, the fifth root of 32 is just 2. This one didn't have a negative. And then on part F, we have the negative fifth root of negative 32. Now this is an odd root, so we are going to be able to get a real number. If the fifth root of 32 is 2, then the fifth root of negative 32 is negative 2. So we are going to have negative 2, in other words, positive 2. Now we said earlier that the square root of a squared was a, because the square and the square root undo each other. And that is true as long as you are sure that a is not a negative number. If you'll go back to that slide, you'll remember that we specified that a had to be a non-negative number. But if a is not specified as being non-negative, then you can run into other problems. So let's look at an example. If we have a equals 6, then the square root of 6 squared is the square root of 36, which is 6, so no problem. But if a is negative 6, then the square root of negative 6 squared is still the square root of 36, which is still 6. So here on the first line, the number that was squared under the radical is the number that we got out at the end. But here on the second line, we had a negative number squared under the radical, but we got a positive out at the end. So how can we keep from having this problem with signs? In order to avoid problems, we have to be careful to make sure that this quantity right here, this radical, always gives us a positive answer. So the square root of a squared is going to have to be written as absolute value of a, just in case a might be negative. Now, a lot of times when you're working radical problems, you'll see instructions that say assume all variables are positive, and that's basically code for don't worry about absolute value bars. But if they don't tell you that all variables represent positive numbers, then you'll have to think about these absolute value bars. Let's practice here. So it says find each square root. In parts C and D, k is a real number, but it does not say that k is a non-negative number. So k might be negative. So let's look at part A together. Here we have square root of 7 squared. Well, we know that the square and the square root undo each other and that we have to get a positive number as our result. Clearly 7 is a positive number, so when the square and the square root cancel each other out, we're just left with 7. On part B, we have square root of negative 7 squared. Well, we know that negative 7 squared is positive 49, and the square root of positive 49 is positive 7. So here you see what we're talking about, that when you do the square of a square root, if the number that was under the radical was positive, then you just get that number out. But if the number that was under the radical was negative, then you get the absolute value out. You get the positive of that number. Okay, here on part C, we just have square root of k squared. And it doesn't tell us in the instructions that k is guaranteed to be positive, but we have to make sure that the answer comes out positive. So when the square and the square root undo each other, we have to make sure that our answer shows that the result is absolute value of k so that it's a positive. And here on part D, same thing. If k was positive before, now it's negative. If k is negative, then with this negative in front of it, now it's positive. We still don't know whether k is positive or negative, but we know that the square and the square root cancel each other out, and we know that we have to get a positive result. So the square root of negative k squared is going to be absolute value of negative k, which of course is the same as saying absolute value of k, because either way the value comes out positive. So let's see if we can generalize this idea to any nth root. If n is an even positive integer, then the nth root of a to the nth power is going to be absolute value of a, because the nth root and the nth power will cancel each other out, but you have to get a positive result here. Whether a was positive or negative, the result has to be positive, so you put the answer in absolute value bars. On the other hand, if n was an odd positive integer, then the nth root of a to the nth power is going to be just a, because if a was negative, then an odd power of a will be negative, and if a was positive, then an odd power of a will be positive. So we want the final answer to reflect the same sign as the original a, so we don't have absolute value bars. Basically, if you're doing an even root of an even power, you need the bars. If you're doing an odd root of an odd power, you don't need the bars. Okay, let's practice here. So we have the sixth root of negative 3 to the sixth power. Now the power and the root are going to cancel each other out, but this is an even index, so we need the final result to come out positive. So it's going to be absolute value of negative 3, which is 3. On part B, we have the fifth root of negative 4 to the fifth power. The power and the root cancel each other out, but this is an odd index, so we will not have an absolute value bar here, so the fifth root of negative 4 to the fifth power is just negative 4. On part C, we have this negative in front of the whole thing, so we're going to keep that negative, but then the fourth root of the fourth power is going to cancel each other out, and we're going to need the absolute value bars because of that even index, and therefore we'll have absolute value of negative 9. Now, the absolute value of negative 9 is positive 9, and then we'll still have this negative out here, so we're going to end up with negative 9 as our final answer here. On part D, we have negative square root of m to the fourth. So we're going to have a negative in front of our answer, and then the square root of m to the fourth would be m squared, because m squared times itself makes m to the fourth. But because this is an even root, we're going to put that in absolute value bars. Okay, notice m squared times itself is m to the fourth. Notice we have the bars because this is an even index. Notice we have this negative because we had a negative in front of the original radical. All right, now let's think about this. Do we really need these bars? Because any number times itself is already going to be positive. All the absolute value bars do is turn the answer positive, but this answer is already guaranteed to be positive. So we really don't need these bars, so we will keep this negative, we will lose the bars, and we'll just have negative m squared. Here on part C, we have the third root of a to the 12th. So what could I multiply times itself 3 times and get a to the 12th? Well, we know that a to the 4th times a to the 4th times a to the 4th would be a to the 12th. So the third root of a to the 12th is going to be a to the 4th. And I do not have absolute value bars here because this is an odd index. And even if I did have absolute value bars, a to the 4th is guaranteed positive anyway. Okay, on part F, we have the fourth root of x to the 12th. Okay, so here we had third root, now we have fourth root of x to the 12th. So what could we multiply times itself 4 times and get x to the 12th? Well, that would be x to the third. So the fourth root of x to the 12th is going to be x to the third but this is an even root, so I'm going to need absolute value bars around that. So for part F, the fourth root of x to the 12th is the absolute value of x to the third. It may take a little practice for you to get used to dealing with these absolute value bars. Don't let it throw you too much. As long as you keep thinking about it and developing your understanding of roots, this work with the absolute value bars will eventually come to you if you keep after it. Now let's talk about using a calculator to find roots. So remember, whenever a radicand is not a perfect square, the radical expression will represent an irrational number. And because we can't just think those numbers up on our own, if we need a decimal representation, we usually use a calculator. To approximate such roots, we use a calculator. And the word approximate is here because the calculator cannot give you an exact representation of an irrational number. Once you go to decimal form, it's going to have to be rounded off somewhere, and once you round, that's an approximation. For the calculator that we use, the TI-30X2S, you can evaluate a square root by entering a radical and then entering the radicand. To access the square root function, you'll press second x squared, and I've got a calculator video in your course in Canvas if you'll go watch that. To evaluate nth roots, so anything beyond a square root, you'll need to first enter the index and then press second caret to get your radical. So if you wanted the third root, you'd put in 3 and then this second caret symbol, and that would give you the third root radical. Now, like I said, this is an approximation. So when the result of a radical expression is irrational, you will have to decide how many decimal places to round off to. If you're using MyLabs Plus, they will tell you how many decimal places you'll have to keep in your answer. A wavy equal mark indicates that the number on the right side is not exactly equal to the value on the left because rounding has taken place. I know you've seen those wavy equal marks before. That just says, hey, there's been some rounding here, so these two things are not exactly equal. They are sort of equal. So let's use a calculator to approximate each of these radicals to 3 decimal places. Now I can't show you the calculator on the screen right now, but I'm trusting that you have your calculator in front of you and you'll practice entering these yourself. So the square root of 39, so you'll do second, then the square button, and then 39 equals, and when I do that, this is the number that my calculator screen shows. 6.244997998. And of course the instructions say round to 3 decimal places. So the third decimal place is the 4. So we'll have to decide whether this stays a 4 or whether it gets rounded up to a 5. So you look at the next digit that you're not going to keep. The next digit is a 9. If anything 5 or up will cause this number to get rounded up. Anything that's below a 5 will mean this number stays the same. So this 9 means that when I cut off all these extra digits, I'm going to take this 4 up to a 5. So our final answer here is approximately 6.245. Notice the wavy equal mark means we are rounding. So the square root of 39 is approximately 6.245. On part B, we have negative square root of 72. So of course our final answer is going to be negative. I'm not even going to enter the negative into the calculator because I just don't need it. What I need are the decimal places. So the square root of 72 gives me 8.485281374. And notice that even here I've put the wavy equal mark, because even though this has all the decimal places that the calculator can show me, it's still an approximation because there's an infinite number of decimal places here. But I only need to keep 3. So the first decimal place is 4, then 8, then 5. 5 is the third decimal place. The digit after that is a 2. So that tells me that I do not need to round this third decimal place up. My final answer for negative square root of 72 is going to be negative 8.485. and the 5 stayed a 5 because the next digit was not big enough to make it go up. Okay, cube root of 93. So on your calculator, you'll need to put in the 3 and then go second caret or second power to get the radical. So then your calculator is going to say 3 radical, and then you're going to put in 93. So if you do it right, the third root of 93 is going to be approximately equal to 4.530654896. And again, we need to round to the third decimal place, which is this 0 right here. The digit after the 0 is 6. That's big enough to make me round my 0 up to a 1. So the third root of 93 is approximately 4.531. That's our final answer. And then for the fourth root of 39, we put in our 4, then the nth root of 39, and the calculator screen gives us 2.498999,399. And to round off to the third decimal place is an 8, but the next digit is a 9. So that tells me that this 8 is going to have to go up. So the fourth root of 39 turns out to be approximately 2.499. And that's it. We are just getting started with radicals, so I'll see you again next time for section 10.2, and we'll start wrapping this baby up.